Let's switch gears a bit and talk about a slightly different learning problem, face recognition using confidence. In face recognition, we're trying to solve the following problem. Suppose we have a database of people, and given a new image, we want to output the ID of the person that's shown in the image, or simply state that the person in the image is not part of our database. The challenge we're commonly facing in face recognition is few-shot learning. The number of people in our database is usually quite large, while the number of images we have per person is small. That means we need to recognize a person given just one or a few example images. In such situations, it turns out that simply training a classifier is not a good solution. First of all, it won't be good enough to recognize a person from just a few images. And second, every time we add a new person to our database, we would have to retrain our classifier. So one solution here is to learn a similarity function instead of a classifier. At inference time, when we're given a new image, we compute how similar it is to images in our database. And if the similarity is greater than a certain threshold, we conclude that the person shown in the image is present in the database, and we determine their ID by computing the nearest neighbor or vote among the k nearest neighbors. To learn such a similarity function, we can use an approach called Siamese networks in combination with contrastive learning objectives. Let's look at what that means. The input image, x1, is run through a convnet to produce a vector embedding f of x1. And we can do the same thing for a second image, x2, to compute f of x2. The two convnets here share the same weights, which is why we call them Siamese networks. To quantify the similarity between two images, we compute the distance between their embeddings, for instance by taking the squared Euclidean distance. But how do we learn this embedding function? Well, the parameters of this convnet define the function f of x. So we want to learn its parameters in such a way that it maps images of the same person onto nearby points and pushes embeddings of different people away from each other. In other words, if xi and xj show the same person, we want the distance between f of xi and f of xj to be small. And when xi and xj show different persons, we want the distance of fxi and f of xj to be large. We call this learning strategy contrastive learning. This learning goal can be accomplished, for instance, by using a triplet loss. To compute the triplet loss, we need a triplet of images. The first image is called the anchor, and then we have a positive sample showing the same person and a negative sample showing a different person. We embed all three images by using the same convnet, and then we compute the triplet loss. The loss function is given here on the right. Overall, we want to minimize this loss function, so let's look at the individual pieces. The first is the distance between the anchor and the positive example, and we want to minimize it to map two images of the same person to similar locations in the embedding space. The second is the distance between the anchor and the negative example, and because it goes negative into the loss function, we want to make this term large. In other words, we want to map images of different persons onto distant locations in the embedding space. The plus alpha and the maximum with 0 ensures that the distance between negative pairs is greater than that between positive pairs by at least alpha. So in the exercise, we want to visualize some embeddings learned by a face recognition network, VGG face. That's our VGG network that we've learned about earlier today, trained on a face database using the triplet loss we just saw. And we will look at how it separates the images of different people in this embedding space.